Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the PKI Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitoris. Join the discussion. Join the PKI Consortium. Go to pkic.org/join.
Navaneeth Ramachan. Navaneeth is from the IBM Research Lab in Zurich. He's been a senior member of the IBM team there for several years. He's particularly adept and has been working diligently over the last few years on practical applications to affect the transition to quantum-safe cryptography across diverse topologies. And sort of building on that subject of crypto agility, he's going to present a framework for cryptographic agility to the audience today. So without further ado, Navaneeth Ramachan.
Hope it works. Yeah, okay, great. Thanks, John, for the introduction. So my goal in this session would be to build in an incremental manner and hopefully in an intuitive manner the elements that one would need to enable crypto agility. So and in the course of that, I'll walk through a roadmap with interim steps and hopefully some checkpoints that organizations can take to enable crypto agility. So before I start, I just want to make this remark that crypto agility has a number of interpretations. It's a very broad term. So it's not just a technological problem. It's a people and process problem as well. So I'll be focusing specifically on how applications that consume cryptography today can become crypto-agile. So that's the primary focus area. But we will touch elements of governance, visibility, and control through the course of this one potential view into the elements needed for crypto agility. So let's start with this very simple view of what a typical crypto call today looks like. So if you look at it, don't have to understand the code at all. Sorry, okay. So we don't have to understand the code at all, just look at it briefly. So we have a key creation process for ECDSA. Then we perform a signature with the private key, and then we validate the signature with a public key. Now, this looks straightforward at first, but it has a couple of issues. The most important one being that application developers are typically not crypto experts. And as you can see that it has a lot of coupling with crypto properties as a part of it. So this is one of the leading causes of vulnerabilities today that you see, where crypto properties are not used correctly. There is a lot of coupling in there. And the other issue is that we have a number of elements in here that are hard-coded into the application. So specifically, there are a number of crypto properties that are baked into the application, and this is precisely what prevents agility in a view, right? So if any of these inputs change, then the application code has to change too. So this really means that you need to rewrite your application, retest, and redeploy. And this is the churn we want to avoid with agility. So if you look at these inputs, let's look at what these different elements of inputs are. We have the algorithm, we have the hash function, we have the curve, the keys, and we also have some implicit parameters that the crypto library provides, like the signature encoding and also the randomness source. Let's look at these inputs a bit in detail and try to see what we can do about this. So basically what we want to do is to have some kind of decoupling of these crypto parameters from the application code and take away this complexity from the application developer themselves. So if you look at this in detail, we can kind of categorize them into two combinations. One is the parameters that are required for doing the cryptographic operation, and then we have the key bytes themselves. So if you remember, our goal is to try and see how we can do crypto. So we're not doing cryptography differently, but we want to change where the decision points are for doing cryptography. Take it away from the application, but into an abstraction layer of sorts. So we can imagine an abstraction layer that consumes crypto, but this abstraction layer kind of encompasses both the key and the parameters under some sort of a named identifier. So once we do that, then we could potentially do something like this. So previously, there was a lot of knobs and dials to do signature operation. So now we have something rather simple. So what we are trying to say is that an application developer shouldn't need to know how to do the cryptography. All they need to know is that what needs to be done from a crypto perspective. So with such an abstraction layer, there are bells and whistles around it. We can talk about it. But in this specific context, we could summarize into something like the application developer needing to know what crypto operation they need to do. So it's a signature operation. And for a signature operation, crypto 101, all you need is the data and the key to do the signature operation. So can we kind of distill the crypto operations to the bare minimum that is required? So with this abstraction layer, all we would say is ask the abstraction layer to sign, provide a key identifier. It's a named identifier. It could be a UUID. It could be a name. It has to be unique is all that is required. And that kind of points to the parameters and the key bytes themselves. And you could just ask to sign your data. So this would really decouple the app from crypto specifics. And with this, we could start looking at the first element of what a framework would entail. So the first thing is an abstract API. So, and as we go through the deck, we will see that we will try to build on top of these, the different elements that one would need in order to get towards crypto agility. Now, the moment we have an abstraction layer that kind of captures the key and the properties, we would naturally want to manage the lifecycle of the key. So, and there are these typical lifecycle elements where you do key creation, key storage, key revocation, deprecation, and also destruction. Right? So those are typical key lifecycle management elements that it's good to do that. We don't have to do it, but it would be good to do it, and we'll see why. So these are the typical key lifecycle management elements. But at this point, we can introduce two more primitives for key management, which might be relevant. And I call this key transformation and key versioning. So just to give an insight into what the distinction is. So when we talk about key rotation, so if we take, for example, an ECDSA key, a rotation of an ECDSA key means the properties of the key are retained, so it's still an ECDSA key, but the bytes of the key change, right? So that's a rotation typically, right? So the key properties are retained, but the bytes change. But because we do key management, we could do something called a transformation. And the idea with the transformation is that you take an ECDSA key, so you could potentially transform the key from an ECDSA to MLDSA. So the idea there is you're not only changing the key bytes, but you could also potentially change the crypto properties of the key. And once we talk about changing keys and moving between different types of keys and key bytes, it's also wise to introduce a thing called versioning, because we want to track provenance, and it would be good to maintain this invariant of immutability. So anytime you change a state of a key, you want to move over versions. This would enable some nice properties like backward compatibility. So with key management and this introduction of transformation and versioning, it sets up very well, as we will see going forward, to an agile abstraction layer. Now, what have we achieved so far? At a very bare minimum, already with this, we have what we can call basic algorithm agility. So this could apply for most crypto operations like sign, verifies, encrypt, decrypt, HMAC, so on and so forth. But what we haven't really done so far is kind of talked about how does this key identifier, the parameters and the key bytes come into play. We haven't really talked about how this is being created. So the question is, how do we create the key? So we've figured out how to do this for sign and verify at a bare minimum. But to create the key, we could do one of the following things. So what we want to achieve is have a named key identifier, associate with it the crypto properties for the key. So we could have defined something like a key template, which basically contains all the properties that are required. So in the previous case, it was an ECDSA key with P256 curve, and you needed SHA-256 as a part of the signature operation. So we could create a template that says ECDSA P256, SHA-256. While this would work, if we go back to our goal was to prevent application developers from having to know the intimate details of crypto. So you're still kind of expecting an application developer to know what are the right templates to use. While this is good because you could have secure templates, secure combinations, we still may want to avoid it, as you would see, for agility. And what I mean by agility in this specific viewpoint is that we want to, as much as possible, avoid the need to rewrite an application when you want to move between cryptography. So we could envision it slightly differently. So when you typically, as an application developer, they're aware of the business logic, they're aware of the goals they want to achieve in crypto, we can think of, so in this specific case, the goal behind creating that key was to do signature operations. So can we define a scope-based view which kind of captures the intent behind what crypto you want to do? So rather than hard-coding key templates, you say something like, I want to create a key, call it my key identifier, my key ID, and the goal there is to do signature operations. So you can have different scopes. So you could say you want to use it for authenticated data encryption, for MAX, for example, and so on and so forth. We could define different notions of scope. So this seems a little better than where we were before. So from before, we are now not having any crypto properties coupled with the application. We have a key identifier. We are just saying what crypto operation we want to do and try to stick to the most abstract way of performing cryptographic operations. Now, the natural question then is, where is the mapping, right? So if we say we want to create a key that's meant for a signature, we still need to know what key type to use, what are the key properties to use. And that's the perfect place to introduce policies. So policy, you can think of this as a rule book for cryptographic behavior. This can be broad. This by itself is a long discussion topic, whether it's imperative, declarative. There are a number of things you can do with policies. But in this specific context, under the hood, you could have essentially a policy that maps scopes to what are the preferred algorithm or the templates. So you could have a policy that states, for signature, I prefer ECDSA P256 SHA-256, but as a fallback, I could have ED24519. But you can imagine different combinations of things you could do with the policy. So the nice thing is, once we introduce policy, that kind of becomes a control plane. So you're not baking in the complexity of specifics into the application code itself, but we are kind of decoupling the properties needed for crypto into sort of a configuration, right? A policy, you can think of this as a configuration. Now, in reality, although we now split it into configuration, we are at a good stage already. At this point, I think it'd be comfortable to say that we've achieved some sort of algorithm agility. So we've managed to do key creations without having to know the crypto specifics. We've decoupled it from the application. We're also able to do a number of crypto operations without having to know the specifics at the application layer. So we've achieved somewhat what we call a crypto object abstraction. So all the crypto objects required for cryptography is abstracted from the application code. Now, going back to the policy, so I said it's a control plane thing, right? It's a configuration. We don't want application developers to create the policy. We ideally want the application developers are responsible for using cryptography. They know what they want to use it for, but they don't know what are the right parameters to configure. That was precisely the problem we started with. So we have usually security teams, security admins, and CISOs who are responsible for knowing what cryptography is allowed within an organization in order to meet compliance requirements and so on. So a very good thing to introduce at this point would be identity and access management. So CISO or crypto admins would set the policies, and application developers would use crypto managed by these policies. The policies become the governance plane at this point. So with identity and authorization, you can have a clear distinction between who's trying to set policies, who has permissions to set policies, and who within an organization can use crypto. But because you have identity and authorization, you can even control what crypto is a specific identity allowed to use, right? You can, and we'll walk through one sample crypto-agile workflow as we see that we build these elements, and we would see how this would look like. So at this point, we could claim we have also enabled the governance and control plane. Because we have identity and authorization, we know which identity is accessing crypto. You have very good control from a configuration plane as to what is allowed within the system. And we have what we could call federated algorithm agility. And by federation, multiple identities within an organization come together and they achieve the goals for crypto agility, specifically focusing on their individual function and not mixing responsibilities across different teams. Now, sorry, I want to go back. This is also a good point to talk about how this enables this CBOM capability. So because we have a policy, we know we can make point-in-time statements about what crypto is a system allowed to do. So you could generate C bombs, but because we have identity, we could also generate O bombs, operational bill of materials. So there's a nice talk that Basil will give tomorrow that dives into the specifics of C bomb, O bombs, and the distinction between that. So while this is good, we've already achieved potentially federated algorithm agility. We are still not there quite yet. To achieve what we call a crypto workflow agility, we still need something we call processing agility. So what is processing agility? It's to do with the fact that where cryptography is executed. So if we go back to our previous example, we had an abstract API, the abstraction layer that's doing crypto for you, but under the hood, it's using some crypto library to do the crypto for you. In reality, the need for agility now is exacerbated by the need to move to post-quantum cryptography. But in reality, most of moving or changing cryptography is to do with compliance needs, but for CVEs within implementations. Think of Heartbleed bug in OpenSSL, right? It was not an algorithmic issue, but it was an implementation issue. So for true agility, we also need to be able to switch between cryptographic implementations. So that's what we call a crypto processing agility. Now, the nice thing is, because we have this abstract API, key management, and policies that we've already defined and have it in the abstraction layer, we have some sort of an abstract API that would allow you to unify different crypto backends. So for example, you could have multiple crypto implementations under the hood. So you could have an OpenSSL crypto implementation, you could have a Golang crypto implementation, but you could also potentially have or abstract this to a PKCS11 backed HSM implementations or a KMS from different cloud providers, right? The abstract API really allows you to unify this, and it becomes a policy time decision as to choose what crypto backend to use. So with all of these elements, I think we could start looking into what a sample crypto-agile workflow would look like. So let's take this example. So on the left, we have 3 different identities. So we have a CISO, who's responsible for setting the policies within the organization. We have a signer client. So think of it as a microservice wall. The signer client is responsible for doing signature operations. So a use case is payment transactions coming in. So they just sign this particular microservice, gets the payment transaction, creates a signature, stores it in a database, and then the workflow goes through. At some point, there is a verification microservice that pulls the signed transaction, verifies the transaction, and then goes about its business logic. Because we have identity and access management, we can clearly separate responsibilities. So let's look at one workflow, right? So the CISO officer initially, with this abstracted crypto service view, would inject a crypto policy that allows ECDSA and MLDSA in this case, just making some example. Now, the signer client, when it receives a transaction, would, via this abstracted API, not having to know what is the algorithm under the hood, say that I want to create a key and specify the scope as signature. And at this moment, let's assume ECDSA was preferred. So ECDSA would be the algorithm that it uses. And then in step number 3, abstract API again, all it says is I want to sign, this is the payment transaction I have, that's the data for me, with this specific key identifier, and you get back a signature. In step number 4, as the workflow goes through, the verification client would fetch this from the DB, for example, and then verify the signed payment transaction, again in a very abstract manner, just with the signing key, and things go through. So until step number 4, what we've really achieved is crypto offloading with abstract API and policies, but haven't really seen where agility comes into play. But the nice thing, because of all these different elements that we have, although we don't really talk about the crypto processing backend in this sample agile workflow, up until the authentication element in the framework, the nice thing a CISO office could do, and I've called it out explicitly here, they could do an operation like transform for any reason. Say the organization needs to migrate from ECDSA to MLDSA. All they have to do is say, transform the specific key ID from ECDSA to MLDSA. It doesn't even have to know what it was before, but say transform it to MLDSA. In reality, we don't want CISO to know about different key IDs and all the different keys that exist in the organization, but rather this would be something declarative. So you could have a policy where you say that ECDSA is not allowed, and the system kind of self manages the keys and upgrades them to MLDSA. Now, once the CISO does this in step number 5, then in step number 6 and step number 7, as you would see, they're exactly the same as step number 3 and step number 4. The API hasn't changed. All of these nice abstractions that we have and policies we have allows the application code to consume cryptography without having to rewrite their code. So they just do simply again assign and verify, but instead of getting an ECDSS signature at this point, you would have an MLDSS signature. So that's how we get an agile workflow. And we need versioning here because versioning allows you to attach metadata with the ciphertext that you produce, which means the previous signed payment transactions with ECDSA would still be verifiable, and you could control via policies as to what level of versions you want to allow and have this nice provenance chain as required. So very briefly, so what would the adoption path for organizations look like? This is one way to look at it. There would be other ways too. The first thing to do is try and see if you can replace direct crypto calls with an abstract API. So have a notion of an abstraction that kind of decouples the crypto properties from the application code itself. If possible, centralized key lifecycle management that provides a lot of nice properties like key transformations, versioning, that really allows agility at that point. Then if you want identity and authorization, you have scope-based policies. And at that point, you would have what we call federated algorithmic agility. And then you could finally enable crypto backend flexibility to really respond to critical migrations just in time and not have to wait for system to catch up. So with that, putting it all together, there are also other elements we could do with crypto agility. So we could, in this framework, we can think of audit, provenance, hybrid combiners. What would that look like? But this then would be a much longer talk. So I'll stop here and I'm happy to take questions. Thank you.
Thank you. Questions online? Not yet? Okay. Questions from the audience?
So in this framework, how do we consider about backward compatibility and real-time migration? Let's say, so there's a number of client applications that uses a single signing algorithm and they want to migrate to another algorithm, but we can't do it at once. So there'll be a grace period that we need to support both of the algorithms. How can this framework support that? Thank you.
So the way we look at it is that you at some point you can start with adopting each of these different elements, but you could also so the question is about incremental adoption of different signature algorithms or different algorithms, right? So once you define an abstraction layer, you've kind of removed the need for knowing what algorithm is used. So existing data that's previously signed or encrypted would have to have this metadata associated. So you could have some sort of a migration plan or procedure or tooling in place that would then associate this metadata, or you could import your existing keys into this abstraction layer that then assumes a specific metadata for versions. So this would be one way to enable that transition as I see it.
Thank you for the presentation. My question is, do your framework will transform into a standard to be followed, or your framework will be proposed as a standard to be followed by crypto library implementers, so it become a nice and standard way to implement the crypto agility in future?
That's a great question. Ideally, we would like to standardize this abstraction notion of an API, so that it is also not a vendor lock-in, right? So everyone could define their own notion of what an abstraction is, but at some point that becomes a vendor lock-in. So great point. So we need to look into ways to standardize what this abstraction would look like. Yeah, absolutely.
How do you see the existing solutions available for like Azure Key Vault or AWS KMS? How do you see that in terms of achieving crypto agility?
Right. So if you think of KMS, typically they have, if you look at these different elements, right? So they typically have only one crypto backend. So there is no notion of crypto backend flexibility. It's either a HSM in most cases. So you can't switch between implementations. Although they have identity and authorization, they don't, they have policies at a different level. And they don't really have abstraction the way we've talked about abstractions. They don't have this notion of transformation. So if you've written an application using one of these APIs to do crypto, it is not easy to migrate to a new algorithm without having to touch your application code. So our goal is always trying to see how do you not rewrite, retest, and redeploy. So can we avoid this? And I think in most of those cases, that is not easy to come by. They still have some kind of a coupling.
How does your model take into account dependencies on physical crypto hardware? For example, pushing the software to devices with a TPM with no support for MLDSA, or HSMs with support for certain cipher suites and not others. Like, how do you handle that in your model, the physical constraints that may be used by crypto libraries?
Right. So if I understood your question correctly, it's about a crypto backend, for example, not having support for certain algorithms. At that point, we really don't have much of a choice, right? So we are really reliant on the physical backend that we use to provide the support that we need. Provided there is support, the policies would then enable you to make that transition. But if there is no support, there is nothing much you could do. What this framework tries to do is, given support from the backend, give you a framework to handle the transition without having to go and retouch or rewrite application code. Yeah.
Navaneeth, we have one more question online.
Sure.
Yeah, there's one online question. How does separating the policy from the implementation improve security and operational flexibility?
Right. So, like I said, as I mentioned briefly also during the presentation, we don't want application developers to know the crypto specifics. So we want the crypto specifics to be handled by a team that understands the crypto specifics. It's either a security team or a CISO office. So having policy is that decoupling that happens from the configuration plane and the data plane. So that's really what it helps with. So if you do not make that distinction or make that separation with policies, then having to change crypto is again going back to touching your application code and rewriting the application code, which is precisely the problem we started with. So this is an important factor if you want to achieve algorithmic agility in its true sense.
That's all the time we have for Navaneeth, so please, thank you.
Thank you.
All right, well done, well done. I can say from my experience in the industry, the term crypto agility is the most misunderstood or the most misapplied. Thank you very much, Navaneeth, for your expose on both the subject and a practical framework for applying it. Very intriguing and very interesting.
How do you get to a quantum-safe state? That depends on the current state of your digital security infrastructure, as well as your level of visibility, control, and automation over those systems. Check your level of preparedness with the Entrust Post-Quantum Readiness Assessment. Whether you're already on the path to quantum safe or just beginning your journey, Entrust can equip you with the right knowledge and solutions. There are many paths to a quantum safe future. Secure yours by taking the Entrust Post-Quantum Readiness Assessment today.